Hi, welcome to Statistics 1, Lab 6. In this week's lab, we'll do a lot of the same things that we've done in previous labs. So we'll read a data file into R, we'll start with summary statistics, and we'll do some correlations, but the emphasis again this week will be on regression analyses, and in particular, we will look at regression analyses that include a categorical predictor variable, because we haven't done that yet, and that was one of the things that was covered in the lectures this week, is how to deal with categorical predictors and how to use dummy coding. That is, how to take a nominal variable and convert it into a series of numeric codes that we can insert into the LM function. So that's the novel piece of this lab. I'm using an example that's similar to the one I used in lecture. So the outcome variable will be annual salary of faculty members. But note that this is a different data set. I made up a new data set to illustrate here in R. So you'll see the salaries are much higher now. I sort of did this to reflect more current annual salaries among faculty members. And these are more experienced faculty members. You'll see their ages are higher. So the predictors are age, number of years as a faculty member, number of publications, and which academic department the faculty member comes from. So history, psychology, or sociology. And that's the categorical predictor, right? Because that's a nominal variable. It's just different categories. So we need to represent that somehow via dummy codes, and I'll show you how to do that in R. And the sample size in this example is just 100. I just made up the data. Okay, so again, at the outset, I want to do these basic things. Check your working directory if you need to, set your working directory, and so on, and load packages. So let me do those things. I haven't done that today. That all worked fine. Okay, so now we're ready to read the data in, and I want to actually look at this data and show you what we're dealing with. So let's do that. So you see we have salary. It starts on the lower end of 60,000, goes up to a higher end of like 130. Actually, it goes well beyond that, almost up to 200,000. So you'll see in a minute when we look at summary statistics, these faculty members are on average about 50 years old with a lot of experience and a lot of publications. But what I want to point out here as we look at the data file is this department variable. It's just a character vector. So P stands for psychology, S for sociology, H for history. So obviously we can't enter that into the LM function. R needs a numeric value to put into the LM function. So we'll use dummy codes, and there's an easy way to do that in R. So let's go back to the script. First thing I want to do is just look at some summary statistics and correlations among the main variables. So first, let's look at the summary statistics. And you'll see that, as I mentioned, these faculty members are a little bit older than the example I used in lecture. So the average age is about 50. They've been faculty members for quite a while. They are publishing at a pretty high rate, so an average of 67 publications. That's pretty good. And the average salary is $133,000. So this is a sample of 100 faculty members that are doing pretty well and are a little bit more established. So let's go back to the script. I can do correlation analyses on the main measures. I'm just doing the data frame FS 1 to 4 because the fifth column was department, which is a factor that wouldn't enter into the correlation analysis. And you see that everything is highly correlated and positively correlated, and that makes sense, right? Because especially for age and years, which I'm going to show you are basically redundant in many ways. So age and years are highly correlated. The more years you've been a faculty member, the higher your salary, right? Hopefully you're getting annual raises. But also, the more you publish, and this is true in academia, the more you publish, the more marketable you are, the more well-known you are. You typically make more money if you're more productive in terms of research. So there's a positive correlation there as well. Okay, so let's go back to the script and start doing some regressions. I called this first model just model 0 because I just want to show that years as a faculty member and age of the faculty member are largely redundant, right? They're representing almost the same thing. They're slightly different. You know, people get their PhDs at different times. They join faculty at different times, but for the most part, not by very much. So this is an important lesson for multiple regression is we don't want to just throw in all the predictor variables that we have at our disposal. We want to include variables that are theoretically meaningful, and we don't want to include variables that are redundant. So that the purpose of this first model, and that's why I'm calling it model 0, is just to illustrate that point. So if I run this model, what you see is years as a faculty member, that is a significant predictor of salary, but age isn't. Because they're largely redundant, one of them is not going to have is not going to explain a significant amount of variance in the outcome when the other one is in the model, because they're both sort of explaining the same variance. And years as a faculty member is the more meaningful variable here. So in the models going forward, as I say here in my comment, we're just going to use years as a faculty member and leave age out. I just wanted to include that to show that in multiple regression, it's a bad practice to just throw every variable at your disposal in the model. You don't want to do that. Okay, so now let's look at the models. First, we're going to do model 1, predicting salary from years. Then model 2 will predict salary from publications. And then in model 3, we'll put them together, and we'll see if putting them together does better than having them by themselves. So first, let's look at model 1. So in model 1, we see that we get a significant slope. We could have predicted that based on the nice strong positive correlations, right? So for every 1 unit increase in years, the predicted change in Y, the predicted change in salary is $2,689 or $2,690. And the t-value is 8.4 or 8.5. It's a low p-value, so we would reject the null hypothesis that the slope is 0. There's a significant relationship between years as a faculty member and salary. Makes sense. And it's explaining a good chunk of variance in salary. So it's explaining 42% of the variance just by itself. Okay. Let's compare that to publications. And again, we know from that strong positive correlation that we're going to get a significant regression coefficient here. So here's the regression coefficient. Here's the t-value. It's a very low p-value. Again, we're going to reject the null hypothesis that this slope is 0 and claim it's statistically significant. Notice the t-value here is 9.68 or say 9.7, whereas the t-value was around 8.5. So for publications, the t-value is slightly higher than it was for years, despite the fact that the slope for publications is not nearly as steep as the slope for years. And the reason for that is the standard error is lower in pubs than it is in years. So that's why you get a higher t-value despite the fact that the slope isn't quite as steep. So that can happen because remember, t is the slope over standard error. Just wanted to point that out. Okay, and publications is also explaining slightly more variance. It's about 49% versus years as a faculty member, which is 42%. Not a lot more, but slightly more. The bigger question is, how do these two models compare to a model where both predictors are included in the model? So let's look at that model. And what we see, if we look at the table of coefficients, is both years and publications remain significant. So unlike years and age, these two variables are not redundant. They're each accounting for unique variance in salary, and our prediction of salary should get better by including both of these in the model over including just one alone. But to test that, we have to compare this model to models 1 and model 2. So that's the final step in this part of the script, is let's compare model 3 to first model 1 and then model 2. So does model 3 do a better job? Well, the way we test that is through this ANOVA function that does model comparison. It returns an F statistic, which is sort of like a T statistic. We'll cover this more when we talk about analysis of variance. It's just a ratio of variances, so it's a ratio of variance explained in the two models, and it gives you a p-value, which is based on a sampling distribution, which is based on degrees of freedom, and it's significant. So what it's telling us is model 3 is significantly better than model 1, and likewise it's telling us that model 3 is significantly better than model 2. Okay, so including both years and publications in the model seems to be the best approach. Okay, now let's move to the new piece, adding a categorical predictor into this type of regression analysis. So we already have years and publications, but now we want to look at salary differences across departments. So the way I'm going to do that, and as I noted in this comment here, remember in R there's almost always more than one way to solve a problem, and that's true here in dummy coding or doing contrasts. So I'm just going to show you one way. When we get to moderation analyses next week, we'll actually try this another way. But for now, this is sort of the simplest. We can use this function C, which stands for contrasts, and don't confuse this with little c, which was combine or concatenate, right? This is big C, capital C, for contrasts. What it does is it takes a categorical variable, and this argument treatment will just take the first department, and by first I mean the first one alphabetically, and make that the reference. So the first one is history. So in this example, in this analysis, history is going to be our reference group, and then it will create dummy codes automatically. We don't have to create new columns or anything. It'll just create dummy codes for psychology and for sociology. So I can just run that little piece of code, and it's not going to return anything, but it didn't return an error. That's good. So now I can enter it into a new model. Let's call it model 4, where we have years, we have publications, and now I'm just going to put in this department code, and you'll see that this represents our dummy codes. Let me show you what it looks like. So now we have our slope for years, which is not that different from what we saw before. Our slope for publications, not that different from what we saw before. They're still both significant. But now we have these two new coefficients, and this is the new piece that we need to learn this week, and I covered in lecture, and is sometimes a little bit confusing for people when they first do this. So remember that by setting up this department code and using this argument treatment, what R did is it took the first group alphabetically, which is history in this case, and it made that the reference group. So what that means is across the dummy codes that R automatically generated, history just had zeros across that. So this value right here, 62,000, is the predicted salary for a faculty member in the history department with an average number of years as a faculty member and an average number of publications. So what are these values here? Well, this is the predicted difference between history and psychology, taking into account average number of years and average number of publications. So what this is telling us is the predicted salary for psychology is slightly lower than it is for history. It's not a significant difference, but it's slightly lower. But look at sociology. That's a big difference. It's $18,000 less, and it's a significant difference. So what this is telling us is that the sociology faculty group is making less money than the history group, and it's a significant difference. But that's while we're considering years and publications. And we're now explaining 58% of the variance in salary. I also want to point out that for each of these models, I didn't note them earlier, I've been printing the confidence intervals. Okay, so just one thing to notice is for years and for publications, these confidence intervals don't cross 0. In other words, they don't include 0. So that's an indication that they're going to be significant. Here, comparing history to psychology, it does cross 0. So the interval includes 0, so that's most likely not significant, and that's illustrated here with this p-value. Okay. So let's do a model comparison to see if adding department improved the fit of the model. You should be able to predict this, that it does, because there was a significant difference between history and sociology, right? But let's formally test it with a model comparison. And sure enough, there's the f value, there's the p-value, right? So yes, this model did get better by adding department. And we knew that because one of our predictors here is significant. Okay, so let's examine this mean salary difference a little bit more closely. So if you want to just look at the actual mean salaries for the departments, you can use this function called tapply, which gives us a table for this variable, for this categorical variable, it'll give us the mean salaries. Because the predictions in the model are not the actual mean salaries. So let's just look at the mean salaries. So, I left out my comment, but this still worked. So if we look at the actual means, right, these are not predicted means, these are just the means of salaries for history professors, psychology professors, and sociology professors. And here we see something that's sort of puzzling, given what we just saw in the multiple regression. Right? They're not that different. So 137,000, 129,000, 135,000. So particularly between history and sociology, they're not that different. It's only 2,000. Yet the predicted difference was 18,000. So what's going on? Well, as I say in my comments here, the actual means are not that different. So there must be differences across departments in years and or in publications, because remember, the model assumes an average value of those. So let's check that out. We can use this, again, this tapply function, and we'll do it for both years and for publications. So here it is for years. You see history, an average of 22, psychology, also 22, but sociology, 27.5. So the sociology professors have been working much longer. Also, look at publications. For history, 63, for psychology, about 60, for sociology, 76. So the sociology professors have been working longer and they've published more, yet if you look at their actual salary, they're just on par with history. So that's why when we predict salary based on average number of years and average number of publications, it appears that sociology is underpaid, right? That's what the multiple regression model is showing. So if we had only considered just average salary across departments, we wouldn't have detected this sort of discrepancy that's happening across these academic departments, right? Sociology has been on the job more, they publish more, yet they're not being paid more. The multiple regression analysis that we conducted reveals that discrepancy across departments. And that's one of the sort of powerful things that you can do with a multiple regression analysis, but it also illustrates the care that you have to take when interpreting regression coefficients, especially when including categorical predictors. So let me just go back to the script. I'm basically done with this lab. I just added a summary statement at the end because I know this can be a little confusing the first time you go through it. So there's the conclusion and the lesson at the end. So if you want to run this script again for yourself, you can try it. And this will be, this example is a good one for what you will have to do to complete assignment 6. So that's it for this week. Good luck on assignment 6, good luck on the midterm, and I will see you in lab 7.